Here is a question. Read it carefully and think about the answer. Let us solve it step by step. Let us begin solving this step by step. The starting material is methylene-cyclohexane, which is a cyclohexane ring bearing an exocyclic methylene group, is equal to CH2 at C1. It is a terminal alkene, exocyclic double bond. Moving on to the next step. Concentrated or dilute HNO3 can act as an oxidizing agent toward alkenes. For a cyclic alkene with an exocyclic double bond, oxidative cleavage of the C is equal to C bond occurs. The exocyclic is equal to CH2 is cleaved off as CO2 or formaldehyde formic acid level oxidation product, and the ring carbon that bore the double bond is oxidized to a carbonyl group. However, since the double bond is exocyclic, cleavage opens the exocyclic bond, the is equal to CH2 and gives CO2, fully oxidized, and the ring carbon C1 becomes a ketone carbon. But C1 is part of the ring, so it becomes a ring carbonyl. Yet, the ring itself is intact with 6 carbons. Wait, let me reconsider. Moving on to the next step. Methylene-cyclohexane has the structure where C1 of cyclohexane has an IChO is equal to CH2. Oxidative cleavage of this exocyclic double bond by HNO3 gives the is equal to CH2 fragment oxidized to CO2 or CO, and C1 of the ring becomes a carbonyl. Since C1 is within the 6-membered ring and now bears AC is equal to O with 2 ring carbons adjacent, this would give cyclohexanone. But that is a 6-membered ring ketone, not listed as an option matching answer C. And for the final step, HNO3 can oxidize cyclic systems more aggressively. Consider that HNO3 oxidize methylene-cyclohexane via oxidation of the exocyclic double bond leading to ring contraction or ring cleavage. The nitric acid oxidation of methylene-cyclohexane gives a dicarboxylic acid, A, by oxidative cleavage of the ring through the exocyclic alkene. The double bond cleaves to give a ketoacid or diacid. Specifically, oxidative cleavage of the exocyclic C is equal to C of methylene-cyclohexane gives OHC- CH2, 5-6 oxoheptanidioic acid type, or more precisely opens to give a 7-carbon chain with terminal acid aldehyde groups, CH2, 4-CO or adipaldehyde acid. Actually, the cleavage of the exocyclic double bond in methylene-cyclohexane gives one fragment is CO from is equal to CH2 and the other is cyclohexanone. But if HNO3 further oxidizes and opens the ring double bond being attacked leads to a dicarboxylic acid. Methylene-cyclohexane treated with HNO3 undergoes oxidation. The exocyclic alkene is oxidized, D is equal to CH2 becomes CO2, and the ring C1 carbonyl with the ring intact gives cyclohexanone initially, but further oxidation by excess HNO3 opens the ring at C1, the most oxidized site, to give a linear dicarboxylic acid. The ring opening of cyclohexanone by HNO3 gives adipic acid, hexanidioic acid, CH2, 4-CO. This is product A, adipic acid, A dicarboxylic acid, reacts with Ca, O, to form calcium adipate, the calcium salt. Upon dry distillation, pyrolysis, of calcium salts of dicarboxylic acids, cyclic ketones are formed. Calcium adipate, calcium salt of hexanidioic acid, 6 carbons, upon pyrolysis loses CaCO3 and forms cyclopentanone, 5-membered ring ketone. This is the classic industrial synthesis of cyclopentanone, calcium adipate, heat-cyclopentanone plus CaCO3. A. Cyclobutane would require a 5-carbon diacid, deuteric acid. B. Cyclopropanone is not formed this way. D. cycloheptane would require a 8-carbon diacid, suberik acid. Adipic acid from cyclohexane ring opening gives cyclopentanone specifically. Therefore, the correct answer is C. Therefore, the correct answer is option C.